In this video, we are going to discuss the different types of graphs. There are a lot of different types of graphs, but we are going to primarily focus on five major categories of graph that are most commonly used. The first one is this idea of directed versus undirected graphs. So the graph on the left, which is this one, is an example of a directed graph or a digraph, while the graph on the right, this one, is an example of an undirected graph. Some graphs might have both directed as well as undirected edges, but those are like much less common. So we won't be like throughout this course, we'll be just talking about either the directed ones or the undirected ones. We won't be talking about a mixed graph. So a directed graph will have all the edges that have some direction associated with them, while an undirected one have no direction to any of the edges. You can also convert an undirected graph to a directed graph by replacing each edge with two edges, one pointing uh, to to a node from another node, and the other one pointing from another node to another node. The second type of graph is weighted and unweighted, which is the left one doesn't have any weights that are associated with the edges, while on the right, this one has some weights associated with each edge. Now, again, like you see all these different graph types commonly for different problems. Like, let's say if we are trying to solve a particular problem, such as an example could be a map or a road network, we need to represent this by a weighted graph because let's say if we have two cities like Gainesville and Orlando, and we are there's a connection between Gainesville to Orlando by a road network, they might have some distance that might be used as a weight, which is like how far is Orlando from Gainesville. While on the left, which is this graph, which is unweighted, you also see those in examples, which is an example is let's talk about the World Wide Web, which is each node is represented by a website and two nodes are connected if there's a link from website A to website B. But there's no weight associated between like what is the value of the weight between A and B. They are just like connected, or like Wikipedia links, they are connected to each other, but there's no weight associated with it, like unless we are using some algorithm. The third type of graph is connected and unconnected graphs. So on the left, we have this example of a connected graph, and on the right, we have an example of an unconnected one. So a connected graph has all nodes or all vertices connected, like there's a path from one vertex to another for all nodes. While in an unconnected ones, there might be some nodes which might not be connected to all other vertices, or they might not be a path from one vertex to some other vertex, which is there's no path between C and D in this case. The fourth type is this idea of cyclic versus acyclic graphs. So on the left, we have a cyclic graph because A, B, D, and E form a cycle. While on the right, we have an acyclic graph, although like it might look like a cycle, but if we see like this is a directed graph and there's no path between like A, B, E, D, and A. It's actually A, B, E and A, D, E, like two separate paths. So, like all trees, when we discussed, were acyclic, but that doesn't mean that all acyclic graphs are going to be trees. So, all acyclic things is not trees. Like in this example, this is not an example of a valid tree because there are like two edges that point to E, which is in this case B and D are both pointing to E. So this is, although it's an acyclic graph, it doesn't necessarily means that it's a tree. The last graph type that we are going to discuss is this idea of dense versus sparse graphs. So the density of a graph is defined as the ratio of the cardinality of E, which is the number of edges, to the number of vertices square. So it's basically something like this, which is E upon V square. Now, this cardinality is like the density. Like if we take this density, if it is closer to 1, that means it's a dense graph, and if it is closer to 0, that means it's a sparse graph. So in this case, we can assume that for the number of edges, the maximum complexity or the number of vertices that the upper bound on the number of vertices is going to be roughly O of v square for a dense graph, and the number of edges will be typically equal to O of v, which is edges will be equal to vertices in case of a sparse graph. So I'll give you an example for this, which is in this case, the left one is a sparse graph because we have one node connected to maybe just another node by one edge. Like in this one, we have around 3 edges and there are 4 vertices. So it's roughly equal. It's not necessarily has to be equal, but the assumption is the number of edges is close to the number of nodes. On the right, we have an example of a dense graph because each node is connected to every other node by a vertex. Like you can see, A is connected to all of these. Next, we have B that is again connected to D, A, and C. And then C is connected to all of the other ones. And D is connected to all of the other ones. So the idea of this dense graph is that one node is if a node is connected to almost all the other nodes, it's going to be a dense graph, and if it is not connected, it's going to be a sparse graph. Like if there's minimal number of edges between like one node to all other nodes. So this idea of sparse and dense, you will be seeing in a lot of problems because that influences how we represent graphs in C++. Now, when we talk about directed graphs and undirected graphs, the number of edges, the maximum number of edges that a graph can have, which is when we are just talking about, like, let's say if we are talking about directed graphs, the maximum number of edges that are possible in a directed graph is v times v minus 1. And for undirected graphs, it's going to be v times v minus 1 divided by 2 because in a directed graph, there can be like 2 edges like this, while in an undirected graph these 2 edges kind of like collapse into one. So that's why we divide this number by 2. Like this formula is going to be really useful like when we are analyzing time complexity, and you're going to see again and again, like when we discuss common operations or when we discuss about problems, we are going to define the complexity of our code in terms of E as well as V, which is E is the cardinality of E set E and V is the cardinality of V. So this this comes out of graph theory, and there's a proof for that as well, which is the let's talk about, like, let's say node A. So the maximum number of nodes it can be connected to, like in case of a undirected graph, it's going to be 3, right? Because in this case, if there are 4 nodes, it can be just connected to 3, and we are excluding this idea of self loops as well as parallel edges when we are describing this dense versus sparse terminology. So there's a proof behind it, but you don't need to know the proof. You just need to know the fact that the number of vertices, uh, the number of edges, the maximum number of edges that are possible in a graph is given by v times v minus 1. And that's why like this edges is going to be between 0 and like v square. So for a dense graph, this is typically like, again, like O of v square, while for a sparse graph, this simplifies, like the amortized or the average complexity the of a particular graph is going to be roughly proportional to O of v, because that's the typical number of edges we are going to see. In the next video, we are going to see like an example. I think we'll cover this example and then we are going to see more examples of graphs in the next video. So in this video, like in this example, we have the same picture, which is the image of the RTS app. So this graph, like if we are trying to build this graph, can be represented as directed because there's some paths, like I'll give you an example. Like let's talk about this one. So in this case, there's some direction that is given to it. So it's both directed as well as undirected, because some of the paths aligned here do not have a direction for some reason. So like it's both directed and undirected. Also, it's cyclic because we can see like several places that there is a cycle. Like an example is this one, and it's connected because all the bus stops are connected to another route, which is we do not have one bus stop here while the path ends right here. So all the bus stops are going to be connected to each other. So this is an example of a connected graph. In the next video, we are going to see much more problems, like how different problems can be mapped to graphs, and what are the common operations, or what are the different techniques that are required to solve different graph problems.